All right, testing claims about means. In this example, I'm not asking you to do it in one particular way. I'll go ahead and quickly solve this with both techniques. In a sample of 36 receptionists, the mean age was 43 with a sample deviation of 9.5 years. Use a 0.05 significance level to test the claim that the population average age for receptionists is not equal to 50. Right away, you should be thinking real world situation like that is not going to be true. You can't claim the age of any population is equal to one exact value. I guess you could claim that, but the chances of that happening are very, very small, just thinking about the whole population. Greater than or less than a value, that's more likely, but equal to something in particular, really, really unlikely. But let's go ahead and work through it. The first thing to identify is that we are dealing with a mean here. It tells you right there the mean age. It's asking about the average age, so I know that I'm going to have something to do with mu. The next thing to do is identify the claim, and here I've got my claim, and my claim is going to be equal to that mu is not equal to 50. After I've identified my claim, I'll go ahead and determine the opposite of that claim, and if the mu is not equal to 50 for the claim, then mu is equal to 50 for my opposite. All right, next step is to identify the null and alternative hypothesis. Good thing here, my null hypothesis is always the one with equal sign, so I'll go ahead and identify that. Where mu is equal to 50, and then my alternative is going to be always the one without the equal sign. So in this case, that's mu is not equal to 50. So I've got my null and my alternative. Next thing I'm going to do is identify where my claim is. In this case, my claim matches up with my alternative. That's really, really nice because I know that the keyword there is going to be support. That will show up in my conclusion, and that's going to be very helpful. I also want to identify, because I've got a not equals alternative hypothesis, I'm going to have a test that's going to have two tails on it. So I'll have some value over here on the left-hand side missing low, and some value over here on the right-hand side missing high. Continuing on, I'm going to go ahead and identify my significance level. My significance level here is 0.05. And then I can do this in several different ways. I do need the test statistic no matter what I use. So I'm going to go ahead and calculate the test statistic. The test statistic calculation for a mean is going to be x bar, the sample mean, minus mu, the population mean, all over S or sigma. In this case, because I've got a sample standard deviation, it's going to be S multiplied by the square root of n. You can see that written a little bit different, but that's exactly right what we're going to do here mathematically. Go ahead and identify some of those variables. My x bar is going to be my sample mean. In this case, I've given it to you right here at the top. The mean age is 43. And then my mu is going to be the population mean. I'll identify where I get that in just a second. I'll go ahead and identify my sample standard deviation, which is 9.5. And then I've got to just go forward. The key thing here, I want to talk about this for a second, is where I get this mu value. And I'm looking for the mu value to fill in the test statistic formula. But you can see that I get that mu value from my null hypothesis. I'm assuming that this is true. That tells you right there what that mean value is. Mu value is, so I've got that value of 50. Setting up the formula and solving it will give you this. 43 minus 50 for the numerator divided by 9.5 and then multiplied by the square root of 36. Calculating that out is going to give me a test statistic of 4.42. And this is something that I've skimmed over earlier, but this is really important to identify, that this test statistic is not a z. The reason that this is not a z is because it's coming from the formula with the s, the known standard deviation for the sample. So this is actually a t-score. So this is a test statistic of 4.42 or a test statistic of a t-value of 4.42. What that means is the next step is whenever you graph this on a curve, it's going to have to be the t-distribution, not the normal distribution. This is something we've skimmed over very, very quickly in class, but this is very important. That when you graph this on the curve, it's still going to be the same process, it's just you're using the t-curve instead of the normal distribution curve. So I'll do this twice. I'll do this first with the original technique. So the original technique, again, I've got that normal distribution. In this case, it's just the t-distribution. I'll go ahead and label this here, t-distribution. And that just tells me that I'm going to use the calculator a little bit differently. I'm still going to have my rejection region based at 0.05, where half of it's going to be over here on the right-hand side, 0.025. And I'll go ahead and, I was thinking ahead of myself. I'll go ahead and identify that 0.25, and I'll identify it as RR, because that's rejection region. I've also got that 0.25 on the left-hand side, because that's also the rejection region defined by the lower half. So I've got two values that define that, and I've got to find those values. But in this case, because it's a t-distribution chart, or t-distribution, I've got to look up the calculator for the inverse t. So again, this cannot be done inverse norm like we usually do. It has to be done with inverse t. And on inverse t, what it's going to look for is going to look for the area you're looking for, and then the degrees of freedom. Now, we've talked about the degrees of freedom a little bit in this course, but just to remind you that the degrees of freedom reused is going to be n minus 1. So that's 36 minus 1, so that ends up being just 35. So the degrees of freedom that we're going to use is 35. So this formula really becomes inverse t of 0.025, comma 35. When you calculate that in the calculator, you should get a value of negative 2.03. So this defining value here that defines the rejection region is going to be, I'm going to do this in a different color here. This value here is going to be negative 2.03. Using symmetry, we also know that this value over here on the right-hand side is positive 2.03. I want to point out something really, really quickly that I've kind of glossed over here. We're using an inverse t formula here because this is a t distribution. The reason it's a t distribution is because we're using the calculation for a test statistic that is using S, the sample standard deviation, instead of the population standard deviation. Because we've got the sample standard deviation of S, we've got to use this as giving us a t-score, not a z-score like we've done before. The difference is very, very minor, but you can see right here, this value does make a difference because we're looking at the t value instead of the z value. If you did inverse norm, for example, you're going to get a different value. This same rejection region that's defined by a 0.203, positive and negative, on a t curve would be defined by a negative 1.95 on a z curve. Minor differences, 0.008, but that difference does matter, and I will be able to see if you're doing it correctly or incorrectly on the final exam. All right, let's see. Once I've got that, next step I've got to do is I've got to plot my test statistic. Here's my test statistic, 4.42, so let's come over to my graph. And know that it's going to be positive, it's going to be more than 2, so it's going to be somewhere all the way over here. 4.42. Doesn't matter exactly where it is. All that matters is that it's in that rejection region, and I know that tells me that I can reject my null. So that's a good thing. Let's go ahead and solve this problem additionally with the second format here. Give myself a little bit more room, and I'll go ahead and come in and plot me another curve. In this case, it's a similar curve to the normal distribution, but again, because this is using the test statistic of t-value, this is the t-distribution. Ooh, that was a big T. Let's fix that. This is a t-distribution, and it's going to operate just a little bit differently. So the first step to do with the p-value test, you've got to identify where your test statistic is. So let's go ahead and identify the test statistic. I'm putting it on here twice because it's going to be a not equal to, so I've got two test statistics. We can miss low and we can miss high. So I've got two values. I've got to identify the area of this pink region over here, purple region over above, and the purple region to the left. My curve is drawn very poorly here, but I think you understand the difference here. Next thing I do is I got to identify that area, that region. There's multiple ways to do it. The way I like to do it is using your calculator. So in this case, it's going to be T CDF. It's no longer normal CDF because this is the T curve. And we're going to say, okay, I want to start at that 4.42. I want to go up to 10,000, and I want to figure out given a mean standard deviation of 0 and 1. When you type that into the calculator, you should get a value of 4.55 times 10 to the negative 5. So that's a very, very small number, so I'm telling you that this region is 0.00045 on the right-hand side, and then on the left-hand side is the same exact value, 0.0045. When you type those together, when you add those together, you get a p-value of 0.0009. And again, all we've got to do is compare that p-value over to the significance level. Significance level was 0.05. My p-value becomes 0.0009 when you add those two regions together, because you've got to add both of these. And clearly you can see that the p-value is lower than the alpha. And when the p-value is low, we reject the null hypothesis. This is a good thing because it matches our conclusion from before, so we can go ahead and continue on with our conclusion. Final conclusion, when you type it up, I'll go ahead and add that here. And that final conclusion is right there. There is enough evidence to support the claim that the mean age of a receptionist is not equal to 50 years. Thinking about it this way, we are rejecting the null, right? We're rejecting the null. Well, if we come back to what our null is saying that the average age is equal to 50 years. So we're rejecting that, and we can go ahead and support the claim because the claim matched with our alternative. Because we're rejecting the null. We can't accept the alternative, but we can say, look, we're rejecting the null, and that allows us to support the claim. Number 8 here is hidden kind of a little bit on the page, but I'm going to go and answer it from right here. How is number 7 different from number 6? The big difference here is that they were dealing with two different distributions. One is talking about the normal distribution, and one is talking about the t-distribution. And the reason that is because you've got two different standard deviations given. In shorthand, this number 7 was talking about the population standard deviation, sigma, that was given, and then we had a normal distribution. On number 8, the sample standard deviation was given, that's the S, and then we have a t-distribution. All right, testing claims about two proportions. Males and females were asked about what they would do if they received a $100 bill addressed to their neighbor but wrongly delivered to them. Would they return it to their neighbor? Of the 69 male samples, 52 said yes. Of the 131 female sampled, 120 said yes. Does the data indicate that the proportions that said yes are different for male and female at a 5% level of significance? Not saying a male or female is larger, just are they different? So, first thing I have to identify is that we are dealing with proportions here. It's talking about 69 samples, 52 said yes. That is a success out of total. 69 is total. 52 is the successes. 131 female sampled, 120 yes. That is a proportion. That's screaming proportion to you, and hopefully you're seeing that you've got two samples here. And in this case, what I'm going to do is I'm going to go ahead and call my males sample 1, and I'm going to say my females are sample 2. And I'm going to go ahead and identify some of those terms that I got here, or some of those variables that I got. 69 male samples, that's going to be my N1. That's the number of males in my sample. And out of those 69, 52 of them would return the money. So that's my X1, 52, there we go. My females, my number of females, that's my N2, that's the total number of females, that's 131. And then my X2 is the number of females that would return, that's 120. Again, you've seen here that we're dealing with proportions, so you should be able to see that we're going to have a P1 hat and a P2 hat. And hopefully you can see how to calculate those. You just take your X and your N. So this would be X2 over N2, which is going to be 120 over 131. And then for the males, it's going to be the same idea. You take your X1 divided by N1, and that's 52 over 69. We've been doing this several times this semester. It's nothing different. Let's go ahead and get that. I'll go ahead and give you the decimal values for both of these. So it looks like our male sample comes in at about 75.4%, and our female sample comes in at 91.6%. Now, it's important we remember what we're trying to do in this problem. The problem is not talking about if the female's proportion is higher or lower. The problem has a simple claim. The claim is just trying to determine, are these proportions equal? So the claim is just P1 equal to P2. Now notice that these are not P hat and P1 hat and P2 hat. These are P1 and P2. This is the proportion of the population. So it's trying to make a claim on the proportion population. Going ahead and continuing my pattern that I've done before, the opposite of the P1 is equal to P2, the claim would be P1 is not equal to P2. And that's helpful because now at the next step, when I'm going to go ahead and write my null and alternative hypothesis, I've got them identified for me. So I'll go ahead and come in here and write those down. My null is going to be the one that's always equal, so P1 is equal to P2. And then my alternative is going to be the one that is the opposite of that. So in this case, or the opposite of what I haven't used. So P1 is not equal to P2. And now I've got that. Important thing to identify here at this step before I go any further, my alternative is going to be a two-tailed test. It's going to tell me that it's not equal to, so I'm going to be able to miss high and miss low. I also can see that the claim is going to be in my null hypothesis. So that's nice because then my keyword that I'm going to be using here is going to be reject. Not support like we have in the previous examples, but it's going to be reject. I'll use that at the very end. All right, so now I've got everything set up. Now I can go ahead and solve this problem in two different ways. I can use the t-test, the traditional value, or the p-method value. I'm going to go ahead and do the p-value method here, and I'm going to use my calculator. I've got all the data that I need to just type in. It's all listed right here. So I'm just going to use my calculator and do that. I'll show you what it can give me. So on the calculator, I've got to go to stat, over to test, and then I'm going to go to 2 proportion z-test, because that's what I'm doing here. I typed in my x1, my n1, my x2, and my n2, all listed here on the screen. I go down to calculate. If you want to go to draw, you can see what the calculator is going to draw that the curve for you. But I'll go ahead and calculate it, and I get several values on the screen. The one that I care about the most is going to be that p-value. So I get that my p-value is going to be 0.001, 0.00165. Next step is to take that p-value and compare it to my significance level. Remember, my significance level in this problem is going to be 0.05. And my p-value, I just told you, is 0.0017 if you want to round it up. So which one's larger? Again, patterns kind of follow the same. My p-value is low, and when the p-value is low, my null hypothesis gets rejected. So I've got to reject. If you want to follow it with the other technique, you can. Just a little reminder, what I did to get to this point, I just used a 2 proportion z-test. And why did I do that? You got to think. Well, what am I trying to make a hypothesis test about? I've got 2 proportions, proportion 1, proportion 2. So I'm trying to make a claim about those 2 proportions. Here's another way to think about it. Proportion 1, proportion 2. I'm trying to make a claim about those 2 proportions or support a claim. So I can use a 2 proportion z-test. I got the z-value here of negative 3.14. I've got the p-hat, or the p-bar, but I don't really need those. What I really need is just that p-value, and that gives me enough information to solve the problem and to type up the final conclusion. So there's the conclusion. Using my term reject, there is enough evidence to reject the claim that the proportion of males that would return the money is the same as the proportion of females that would return the money. So we're rejecting that claim. I just cross-referenced this to the key that I printed out. If you want to look at that on paper key as well, I wrote that the claim was a little bit different. I wrote that the claim was not equal to, and looking back to this statement, I don't love this statement. Does the data indicate that the proportions of the yes are different for male and female? That doesn't really have a claim directly stated. So I could see you interpreting the claim as I did here on the video or as I did on the key. So either one, I would be able to grade and accurately and know that I'll be very straightforward whenever I come up with a claim on the final exam. Last part of this test review is going to be talking about testing 2 means. Within a school district, you've got 2 teachers. Those teachers are Miss Jones and Miss Smith. After an assignment, Miss Smith had 30 students, Miss Jones had 25. At the end of the year, each class took a standardized test. Miss Smith's students had an average score of 78 with a standard deviation of 10. Miss Jones' students had an average score of 85 with a standard deviation of 15. Test the hypothesis that Miss Smith and Miss Jones are equally effective teachers using a 10% level of significance. Assume the student population performance is approximately normal. That's important because without that, I can't do this problem. But what I've got here is looks like I've got 2 samples. I've got a sample from Miss Smith's class and a sample from Miss Jones' class. And I have also, hopefully you can see, that I've got 2 samples and I've got their averages. And that's going to be very helpful because when I've got averages, I've also been given standard deviations of my samples. So I've got a situation where I'm going to be comparing means. That's really, really nice because then I know what type of situation I've got. So I've got my 2 populations. I'll go ahead and identify that Miss Smith is going to be my first population, and I'll identify her average test scores as mu1. And then I've got Miss Jones and her average test scores. I'll go ahead and identify that as mu2. So these are the global population scores. Now I want to look at the samples that were given to me. So I've got an average test score of 78 for Miss Smith. That's going to be my X bar 1, that's their average is 78. And then I've got their sample standard deviation. So there's the S1, and that's going to be 10. Then I've got an X bar 2 for Miss Jones. X bar 2, that's going to be, I think it was 85. And then I've got S2, which is going to be 15. Now, what's nice about that is I've got all my data set up. Now I've just got to figure out what and how I'm going to compare these. The one other term that I need, I knew that I was forgetting something. I need the N, my sample size of each sample. So my N1 is going to be 30, and it looks like that was Miss Smith, the number of students she had. And then Miss Jones, my N2 is going to be 25. Now I've got all the information that I need, and I can continue on with the thought process. Again, like we did in the last problem, we've got to go ahead and continue thinking about our claim and what's going on here. So I'm going to come over here right to the side just a little bit of the claim. In this case, my claim is going to be, we want to see that they are equally effective teachers. Well, when I think of equally effective, I think of those means being equal. So the claim is going to be that mu1 is equal to mu2. That's my claim. I'll go ahead and write that out here. My claim. Just following the same pattern that I've always done, I'll go ahead and identify the opposite of that claim. The opposite of the claim of mu1 is equal to mu2 is going to be mu1 is not equal to mu2. Again, it's going to be, now the next step is going to be writing out those null and alternative hypotheses. I'll go ahead and do this with green. My null hypothesis is going to be the one with the equal sign, so mu1 is equal to mu2. And then my alternative hypothesis is going to be the one with the other one that I've got here. In this case, that's going to be mu1 is not equal to mu2. All right. Identifying that my claim is in the null hypothesis is a very important step. That's going to give me my keyword here. My keyword is going to be reject. I will be using that in the final steps. And then I've got to identify, notice that I've got a two-tailed test here because I've got an alternative with not equal to. So that this left region would be missing low, and then this top region would be missing high. So you got those two regions there. That is going to happen. Now, the good thing about these types of problems is I've done everything that I need to do. I've set it up at least. And now what I can do is I can kind of just go ahead and test the claim. And because I've got a calculator available to me, I'm going to use the calculator to test this claim. Here I've got two means, so I'm going to look for my statistical test. So I'm going to press stat, go over test. And I've got two means, so I can run a two-sample z-test or a two-sample t-test. Now, the difference of the outcome is going to be very, very minor, but you've got to make sure you do this correctly. And I'll be able to see, based on your calculations, if you've done it correctly or not. Now, the key here is to identify what standard deviation you've got. If you're confused about this, go look at question number 6 and number 7. There's a small little difference. One gives you the population standard deviation, the sigma. One gives you the sample standard deviation, the S. In this case, I've been given two sample standard deviations, so I know I'm going to be doing a t-test. I don't know what that second letter was. That's supposed to be a T, but I think you got it. Oh, a T. There we go. So I've got a two-sample t-test. It's going to ask me to put in all my stats, and I can do that. After I've typed in my X bar 1, my S1, my N1, my X2 bar, my S2, and my N2, then it gets to a point where I'm asking for my alternative hypothesis. In this case, my alternative hypothesis is talking about not equal to, so I'm going to choose that one. The next option on my calculator tells me if I want to pool the data or not. I'm going to go ahead and say yes, and then I'm going to calculate that. The next screen gives me multiple calculations, but the only one that I really care about for the most part is going to be my p-value. And in this case, my p-value is 0.043. And remember, I've got to compare that to my alpha value, my significance level. In this case, my significance level is 0.10. So for the seventh time on this assignment, my p-value is low. And when my p-value is low, my null hypothesis has been rejected. So I've got rejection here. If you wanted to complete this again with the second technique, you could. But this gives me enough information at this point to type up the final conclusion, which will be, there is enough evidence to reject the claim that Miss Smith and Miss Jones are equally effective teachers.